except you.
Are we? I don't see it live, Tom. Are you sure? Antros, can you see it? Okay, there we go. Oh, that's really trippy. It's are we? I can see myself in the past. Okay, well, I don't see it live, Tom. It looks like we've got 60 people watching, so I think we'll make a start. Hopefully that number will go up in a few minutes, but thank you all for coming along to this event. We're very lucky to have Hugh Hunt and Matt Parker from Stanford here. Okay, there we go. About all things mathematical and some demonstrations, really trippy, hopefully. We'll probably answer some questions, leave them in the YouTube, and Tom, who's controlling the YouTube, will copy them across so that Matt and Hugh can see them and answer them near the end. So I'll hand over to the two now.
Hello.
All right.
Hi, Matt. How are you doing?
I'm good. I'm good. Hugh, how are you doing? This is all very, very exciting, isn't it?
It's normally we'd be sitting at the same table, but we're just going to have to make do with this.
I mean, you're at the same table. This is where we normally are in your room there.
That's true, and messing about with stuff. So whereabouts are you? I'm here in Trinity College, Cambridge, and you are?
I am in my office in Godalming, which is a small town, maybe 45 minutes on the train, southwest of London. It's been a while since I've gone anywhere.
Yeah, exactly.
Near Guildford, if people know that. And so this is it's a bit messy at the moment. I'm doing a bit of a rearrange. And so you can see I've got boxes of kits, and that's like the bits for an automatic knitting machine. Over there's my LED lighting kits down there. There's my backdrop. So I'm in the process of kind of shuffling things around in this space. That's why it's a bit chaotic back there.
Well, it's good to be chaotic from time to time. I'm just chaotic all the time.
Yeah, so true, so true. So normally I would be in Cambridge for one reason or another, and then I would drop by your room. And this originally started entirely just for our own recreational purposes, because for anyone who's unfamiliar, I guess, with either one of our things that we do for a living, we worked together doing talks about mathematics for teenagers. I think that's probably the shortest way to describe.
Trying to make sure that if kids are kind of wondering whether to give up maths after GCSE, we're trying to tell them that there is life after GCSE maths.
Yeah, and they can either continue studying mathematics in the future, I mean, formally or informally, because it's interesting and they enjoy it, or it could be useful in their future careers. And so we do a lot of that. However, we would end up occasionally discussing various interesting bits of, I mean, it's hard to say what the category is, engineering toys.
Well, look, I've got one for you. I've got one for you here, Matt. We've talked about this before.
Oh, there you go. Yeah.
And maybe this will just kick things off. I don't know whether you know what this is.
Oh, is it like a 2-up paddle?
It is 2-up. So 2-up is a game in Australia. I don't know whether you can see these, but these are actual.
They're old Aussie pennies, aren't they?
Old Aussie pennies. But it's a game of chance in Australia where you basically toss the coins up, and no matter which way they land, you lose. I think that's the rule. I'm led to believe.
Yeah.
But one of the questions that we were asking is, what's the chance of the coin landing edgeways up? And we thought quite long and hard about that. And so we got together some bits and pieces. So for instance, if I took a coin which kind of looked like that, not really a coin, but it's just a coin with a lot of thickness. Yeah. And if I toss this up in the air, it's more than likely it's going to land sideways. And it's not going to land like that. So the question was, well, you posed the question there, Matt.
Yeah, I mean, so the question is, if you've got a coin as one extreme end where it always lands face up, one of the faces, and a trivial number of times it will land on the edge. If you get a longer and longer cylinder, it flips. It will always land on the edge, and very occasionally, a trivial number of times it will land on one end. So something like a pen would be the extreme version. Yeah. And so our question was, how thick does a coin have to be so that it's equally likely to land on the edge as either of the two faces?
Oh, I'm up here now on my other camera. I don't know whether you can see the other camera.
No, but I've got
I've got this thing which is kind of what I would have thought was about right. Oh, there's on the edge.
You're still on the coins, Hugh. We're still looking at two.
Oh, no, on the other camera. I've got a second camera.
Oh my goodness! Have I not got your camera coming through?
Oh, there we go. Let me. All right. Yeah, I've got two. I've got a camera out here which I'm waving around.
I've got you. Yep. No, I've got you on the wide now. Yep. Sorry,
there we go.
I didn't have
now.
That.
So on this, I've got what I think is a coin, which is more or less statistically. So that landed yellow, and that's on its side. That's yellow. That's on its side.
Are you keeping track?
Well, I reckon that's about 1/3, 1/3, 1/3. So the question for us then, Matt, is how do we work out the geometry? What do you reckon?
Well, I know you were going to bring this up, but I did grab on my way out of the house my big bag of different thickness 3D printed coins. So a friend of mine printed these up for me when we first got obsessed with this. And the different colors represent different possible thicknesses. So this was part of our can we do it experimentally approach. So we could do all the ones this thickness, see what happens, all the ones this thickness, see what happens. And so we had at one point, I don't know if that one's honeycomb. I don't know if that makes a difference, it being hollow. So we did at one point have, I'm on the wrong side, had the thought, I'm going to swap that. There we go, that's easier. We had the thought of just trying to work it all out.
That's far too clever, Matt. That's far too clever to have a split screen on a Zoom.
I know, I'd like to check that out. There you are. That's what I do. Like a professional. So, but we did come at it from a theoretical approach as well. We had like an upper and lower bound depending on how you model the coin landing. And
well, I think so. The way we looked at it was from memories. If we imagine a coin with some sort of side view of the coin, so that's if you like the head face, and this is the tails, and this is the side. There's one school of thought that says if we put a circle around here, then when the coin lands, that this bit plus that bit would be sides, and then this bit would be heads, and this one would be tails. And so I think that works out that about 1/3 of the circumference is heads, and 1/3 of the circumference is side, and 1/3 is tails, and you can work out the geometry. But didn't somebody else come up with the idea and said, no, you can't do it for a circle. It's got to be done for a sphere. Wasn't that the problem, Matt?
Yeah. Then the other argument was you've not got enough dimensions going on in there. You need to have some more. So actually, when it lands, you could imagine it being circumsphered. And if it lands on the sphere that, covers one face, if that's the contact point, it'll land that face down. If the other half by symmetry, section would land the other way down. And then that band, that kind of curved band that goes all the way around the middle, if it lands anywhere on that band of the surface area of the sphere, then it would land on the edge. And so you need to work out the thickness of the coin such that the band is 1/3 of the surface area of the sphere, which we did work out, and we put a YouTube video out about this. However, that's not assuming, that's like imagining you gently lower the coin down to a surface and then release, and it just plonks down. I don't think that's factoring in the fact that it's tumbling or it's got momentum or any of these other complicated things. And I forget which way around. One of them gave us a lower bound experimentally, and one gave us the upper. I've forgotten which is which.
No, I've forgotten. Well, we have to look at our YouTube video. But I mean, this one, just with the circle, I think you work out that the radius to the thickness is the radius to half the thickness is √3 to 1. And that didn't work. And then when you do that sort of sphere one, where you take a band of a sphere and you have to work out that area, that didn't work either. So where we left this, Matt, do we have to get lots of people out there to do lots of experiments for us?
Yeah, I'm just flicking through my email because I get a ridiculous number of emails sent in saying that where's the answer? People demanding the answer. And so I'm just looking through, and yeah, like there was one yesterday. Like they're pretty constant. So a bunch of people threw different sized coins around, and we got a bunch of data from that, which I have to admit we've not gone through in great detail. I got distracted because I found a paper from the 90s looking at the probability of a coin landing on its edge, and they analyzed the old school £1 coin, which has got a pretty generous thickness to radius ratio. And I then decided to experiment, but they looked at it just being slid off a surface and then dropping onto another surface. I wanted to have the full flipping thing. So I then took an old pound coin and flipped it 10,000 times and tracked how often it landed on its edge. And spoiler, 14 times. So on the order of 1 in every 700 and something flips, it would land on its edge. And it was part of a book I was writing, and it's in the book, but I've got all that footage and I've got all that data. I've actually got the exact timestamp. I've got the starting position of the coin, if it started heads up or tails up. And then I've got the landing position, heads, tails, or edge, for 10,000 flips. And so my idea was because I was doing this coin flipping project anyway, we could use that data and the theoretical work that had been done in the 90s, and hopefully that might give us an insight into what thickness would make it a third, a third, a third. But I've not done anything else with that since then.
Well, the last thing I remember doing with you on this was, how many times did we throw those bloody coins?
Oh, a statistically significant number, I'll have you know.
Yeah. Anyway, look, let's leave coins behind for a second. What have you been working on? What's on your mind at the moment? What new things are you working on, Matt?
Oh my goodness, there's always, we will do a call out for help with the coin project later, by the way. So if that at all interests you, send me an email. I'll send you the data. It's available. I've been obsessed with riffle shuffles in cards. So I thought I would try this live as we go along. I cannot guarantee this is going to work. So
they're coins.
No, that's true. I put them back in the bag so they're out of the way. I have got a pack of cards there. Everything's back to front, depending on how I look at it. And so I did a video. I'm not assuming you watch all the videos, Hugh, but I think a lot of people will have watched a video I did about Minecraft recently, where a player playing Minecraft got ridiculously lucky. Like they just had absolutely improbable amounts of good luck. And so the community of people who keep track of speed runs, they said that the luck they got while playing Minecraft was too good. And they calculated the odds of them having the level of luck they did as being about 1 in 10 to the kind of 21-ish point of probability, which is incredibly unlikely. And so I worked out a kind of a threshold where there's no way it's going to happen in human existence. I worked out the number of seconds 10 billion humans would experience over the course of a century. And I called that the human, I'm going to move that with me so I can be closer to the cards. There we go. The 10 billion human second century. But then a bunch of people started sending in to me bridge results. And there's this crazy thing where people playing bridge had got perfect bridge deals. And the probability, if you get a deck of cards and you deal it out between 4 players, of all 4 players getting a complete suit each is just vanishingly unlikely. It's on the order of 10 to the 30. And so that is way, way, way less likely than the Minecraft stuff I was going on about. And so people said, well, hang on. If this has happened, and this is less likely than what happened to Dream, surely it's possible this could have happened to Dream. And so I thought I would give it a go. And so what happens is I looked at these descriptions. People were playing bridge. They'd get a new deck of cards. You just watched me get a new deck of cards. They'd give it a few riffle shuffles. I just shuffled it twice. And then you can cut it like wherever you want. And then you deal it out for the, oops, drop the bottom card. It's that, just out of interest, right? And then you deal them out into 4 hands. And you can track, is that, can you, let me pan that. You know what, I'll have a bit less of me and a bit more of the cards. There we go. Where was I up to? Do I go on to that one? Nah, I think it must be, oh, what a quinky dink. We're going to that one. And then I did that one. So as you can tell, they're going to be all the same suit. That would be a really disappointing if I forgot where I was up to in my deal and the whole thing broke. But you did genuinely watch me riffle shuffle this deck twice, and then I cut it at an arbitrary point in the deck. And once I've dealt this out into 4 piles, the odds of them all being the same suit is vanishingly unlikely. But sure enough, if you turn over this pile, that's every single one of the diamonds all ended up in the same pile. This lucky person over here, they've gotten every single spade. This lucky person, they've got every single heart. And over here, they've got, I should have used a better surface, every single club. And
but
so
I reckon if I saw the person I was playing bridge with shuffling the cards the way you did, I would, they were a bit dodgy.
Yeah, not wrong. So I need to get better at it. I have taught myself how to do a perfect riffle shuffle. So when I was doing those shuffles, it was perfectly interlaced, one after the other after the other. And so I'm not good enough at it to do it in a super nonchalant way. But if you're very, very careful, you may have noticed, oh, I probably can't get that to focus, can I? Come on, camera, play ball. If it sees my eyes, it auto focuses on them. So I'm trying to cover my face up. The rest of the talk is just, there we go, right? So if I'm super careful, you can interleave one deck with the other deck. So the cards perfectly space themselves out one after the other. Oops, I'm a little bit off there. And a deck, the order it first comes in, if you do 2 perfect riffle shuffles and then do any number of cuts you want, and then deal them out between 4 people, everyone will get a complete suit. So I think it's really interesting that, yeah, the odds are incredibly unlikely. And in fact, it does tell us that it's impossible, that it can't happen because the odds are just so vanishingly small. It turns out there's another explanation for why people were getting these perfect bridge shuffles. And so I thought it was interesting. People were using it as a counterexample to me, showing that this Minecraft player Dream, in my opinion, was definitely not playing on a standard version of Minecraft. And people are saying, hey, well, then this shouldn't have happened either. And it turns out it didn't. Same as Dream. I think there's a different explanation to what happened, because the pure probability, if the game was being played like the standard way, vanishingly unlikely. So that's been my obsession has been learning to do that and looking into riffle shuffles. Well, what's been filling your time since
I think, you know, when you're in lockdown, you do your mind goes on to silly things, but there is something which I don't know whether you've ever thought about, which is about integration. And I'm gonna show you something here. See what you think.
I'm ready.
If you do integrals of things going to infinity, then things go a bit wacky, right? So if I've got a sine wave like this, you're going to tell me that the integral from sine x from 0 to infinity is it's undefined. Or
I'd also accept 0.
Well, okay, you're going to accept 0. So there's my graph of
maybe.
There's my graph of sine x, right? So here's my second question is, what about this one? So if I call this one I1 and this one I2, well, cos x is just exactly the same as sin x, but starting from a different place.
Yeah.
So I would argue that I1 minus I2, whatever the value is, it's got to equal this area. And that area, which is the integral from 0 to pi over 2 of sin x dx, that's equal to 1. So I reckon that that must be true, even though neither of these two things are defined. Now, stop looking at me like that. You're making me nervous.
Yep. No. I mean, the thing is, you're doing the integral equivalent of naive calculations on sets that, like, sequences that don't converge. So if you've got a non-convergent series, you can do all sorts of ridiculousness where you hide something at the bit that approaches infinity, and so you get a weird result at the beginning. But just because you've rolled it out of the way where no one's looking down near infinity.
So I have a tuning fork here, right? Okay.
Yep.
And if I whack it, I don't know whether you can hear that.
Just it's coming through.
There's a sound, but that sound is decaying away slowly. All right. So the sound, it's not going on to infinity. All right. So I was thinking, Matt, that what if instead of doing an integral of sin x, what if I did an integral of e to the minus epsilon x sin x, an integral of e to the minus epsilon x cos x? So these would decay away with this kind of exponential sort of thing to them, right? And it turns out that if I put epsilon into being some tiny number, but still not 0, okay, then it turns out that I1 is very much close to 1 and I2 is very much close to 0. Now, I'm an engineer, right? Okay. And I work in the real world where things actually do stop. Things do decay to. So why can't I use those results in the real world? Because maths isn't real unless it can be applied to the real world. So I'm confident. I'm confident that I can use those results. But you think I'm not?
The very premise of your question, I'm not on board with. The maths can be perfectly valid. I'm also probably not the right person to be asking. I have been accused of integrating like a physicist. So my approach to integration is very much a good enough is good enough. We'll worry about the rigorous details later, which is very similar to integrating like an engineer. However, mathematically, you've got to be very careful how, particularly when you're integrating to infinity, because all sorts of weirdness, as you can see here, right? The areas should be the same. I mean, you're right, slightly different depending on how you look at it. But it's like when you're adding the sequence of 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, infinitely many of those. It's not converging on a
but if I did e to the minus epsilon x multiplied by that. Anyway, look, I'm just gonna finish this one off by saying anyone who wants to check this up for themselves might find it helpful to use e to the minus epsilon x cos x plus I sine x and do the integral of complex stuff. That turns out to be much easier. But that's for anyone who's interested in that might follow that up in their own time. So Matt, what's something else you'd like to talk about?
Hang on a second. My for some reason, my Bluetooth headphone defaulted back to my internal speaker.
Well, we can hear you.
Oh, there we go. I'm back. I can hear you again now. I lost you for. I lost.
Okay. Well, so it's your turn now. So, what would you like to?
What I was going to say is the chat in our Zoom call here is pretty quiet, but I was wondering if there are questions or comments from either people who are watching on Zoom. I don't think I've got access to the YouTube link unless someone wants to chuck that. Oh, here we go.
Oh, well, Sam's here. He can.
Yeah.
He can chuck some questions.
Tom, can you copy across the questions that are coming up in the YouTube for the chat?
Or give me the YouTube link, and I'm not a stranger to YouTube comments. I can.
That's true. I think the YouTube link is at the top of the chat.
Oh. It must have been there before I oh, there.
Oh, right, okay.
Well, I can do that first question that just popped up. Where did you find the willpower to chuck a coin 10,000 times? Emoji question mark. Do you have the recordings of the coin landing on its side? Yes. To both. No, so hang on. I'm opening up that YouTube link and I'm a little nervous. I'm going to suddenly get a weird recursion thing going on. So I'm going to make sure I've muted that. There we go.
I'm doing the same here, so I'm about to get some recursion stuff going.
Mute it. Yeah. So I just kind of thought, you know what, it'd be interesting to do. It'd be worth doing. And so I just sat down, and I put aside 3 days. And at the time I was working at Queen Mary University of London, and so I booked a room in the maths department, like a little meeting room. And for 3 days, I sat there and flipped the coin. And I've got a surprisingly high tolerance for repetitive activities. And assuming that I think the outcome is sufficiently interesting. And in this case, I thought it was sufficiently interesting, partly because I've always wanted to flip a coin that lands on its edge, and partly because I thought it would help me answer this three-sided coin problem that I've had with Hugh. And so I just sat there and did it. And the next question of, did I have the recordings? Yes, so I filmed it. I filmed the whole thing. So I've got hours and hours of footage of me flipping a coin. I had a bit of fun with it. So one time, every time before I flipped it, I said, hi, welcome to my video. Here's how you flip a coin so it lands on its edge. And it landed on its edge. And eventually, I kept doing that.
Didn't you do something like you had a copy of a book or something and you tossed it over your shoulder and it went into the bookcase?
That was a recent video, yeah. And I did a video where I had like a basketball hoop, like a toy one in the background. And during one take, I throw 3 or 4 consecutive shots over my shoulder and they go in. The really fun take was I got some friends involved. And so for some of the flips, I pretended I was making a YouTube video about how it's impossible for a coin to land on its edge. And so the video starts with me saying, oh, I'm here to show you why if you flip a coin, it's impossible for it to land on its edge. And then it lands on its edge. And I'm like, what? And then Steve Mould, who makes science videos, comes walking into the room because he was waiting outside for me flipping it over and over and over again until I finally got it on the edge. He comes in going, right, I'm ready to do that video about how a coin can't land on its edge. He's got like a bunch of maths. And I'm like, no, it just landed on its edge. He's like, no, it didn't. I'm like, watch. And I flip it again. And we stood there until it happened a second time. And so we've got the next take of me going, look, no, watch, I'll do it again. It lands.
Yeah, man.
But then when it lands on its edge, Tom Scott comes walking into the room going, right, how's the video going about how a coin can't land on its edge? And we're like, you just missed it, right? And so we did another take with all 3 of us there. It took hours, but we got it to work. And so I have got all that stupid footage. And once I've got something meaningful to say about the data, we will release that onto the internet. So no spoilers, don't tell anyone.
Okay, won't tell anybody. No one's ever going to know.
We got a question about your boomerangs here, Hugh.
Oh, I've not been paying attention. What's the question about the boomerangs?
Hugh, how many boomerangs do you have in your possession?
Well, I don't know, probably about 20 or 30. You know what the problem is? You must get this all the time, Matt. You know, your
problem is, if you try to throw out a boomerang.
Look, you must get this all the time. You're Australian. Everybody assumes that what you want is Vegemite.
Correct.
And boomerangs.
I'm actually surprisingly low on Vegemite because I'm doing fewer trips back to Australia than normal at the moment. So that's a real problem. But carry on.
Yeah, well, I've got quite a few boomerangs, and but probably about 3/4 of them are just ones that people have given me over the years because they assume that I don't have enough boomerangs. But I like making them, and since it's been mentioned, I've got one of these balsa wood boomerangs here, which are quite fun to make. And I'm just going to throw this in the I'll throw it in the room. You might need to look at the wide shot. So I'm going to see where this is going to. Let's do it this way so you can kind of see the whole thing. Here we go, chucking the boomerang. There we go. Oops, I should have caught that one. Did that come across all right? I can't tell really.
Yeah. No, we can see it hit you. So.
Oh, now it hit the computer.
Table that time.
Right. Third time lucky. This time I will try and catch it. But I hit the computer again. Never mind. You get the idea.
I mean, I can count like 15 boomerangs in that shot alone.
Let's see if I can. Well, there you go. Let me see if I can do boomerang sitting down. Oh, not bad.
Oh, hang on. Surely the harder you throw it, the bigger the circle it's going to go around.
That turns out you're just lighting me up on that one, aren't you, Matt? It turns out that the radius of the flight of the boomerang is independent of how hard you throw it.
What?
So it's quite neat. If you take a boomerang which is going around, this is a plan view. So here I am. Here's the top of my head.
So we're looking down on you throwing the boomerang.
Yep. And that looks more like the top of my head. That'll do. So the boomerang's going to go around in a circle, and the radius of that circle is independent of how hard you throw it. And so the boomerang, if you think about how these boomerangs work, is that if I think of this cross-shaped boomerang, the one that I've just been throwing, the one that kind of looks like that, it's got an aerofoil shape. This is it's like a wing. So that means that when it's spinning, the tips of the boomerang are going around with a certain speed. But if it's also moving forwards, then the bits at the top have got the spin added on to the forward speed, whereas the bits at the bottom have got the spin taken away from the forward speed, which means that if this is a little bit of a wing, it's not moving through the air as fast as this bit of wing.
Slower relative to the air around it.
Yeah, exactly. And so that means that this bit of wing's got more lift than that bit of wing. So if I imagine thinking of my boomerang, drawing it kind of as a 3D picture here, let's see if I can do that. There we go.
I mean, you say lift, but it's sideways to gravity, right?
So there's exactly. I'm calling it lift. It's you've got to throw it in a vertical. You've got to throw it in a vertical plane. So if I go back to me normal camera here, you've got to throw it. When you're throwing it straight up and down like that. Yep. And so it means I've got more lift at the top than at the bottom. And that gives you a gyroscopic effect, gyroscopic couple. And I quite like gyroscopes. It means that gyroscopic effect is what's causing the boomerang to go around at just the right rate around a circle. So there's quite a lot of maths. And by the way, you have to do integrations. Fortunately, you don't have to do the integrations going to infinity.
Thank goodness. I'm actually working on an integration project at the moment. A guy I know just went down to the bottom of the Mariana Trench, so the deepest point of the ocean. And the question I had was, how do they calculate how deep they are? And I mean, the simple answer is they use sonar. The more complicated answer is they're measuring the pressure. And so they need to be able to convert the pressure they're experiencing to the head of water above them. But that's not, like, if you just assume everything stays the same as a nice linear relationship, you double your depth, you double the pressure. But there are several other things that change that. And so I had some fun integrating by getting gravity as a function of depth, and then you can integrate across the descent to work out the pressure depth level, and that gets within a couple 100 meters of the actual true value just by varying gravity.
You have to just that you assume that water is actually compressible.
I assumed it was incompressible. However, I've also now got, then you've got to factor in it's compressible. And I think you can do that in theory. I haven't done that next. That's my next step. You've also got to worry about the temperature because that changes the density. And you've got to worry about the salinity. And so as the submersible goes down, every 10 seconds, they measure the conductivity of the water to get the salinity. And they're measuring the temperature and they're measuring the pressure. And they use the other ones to work out, and you kind of log the density of the water all the way down. And you've got to compensate for the difference in atmospheric pressure, whatever it happens to be at the surface. And you've got to know your latitude, because that will change, obviously, your gravity and everything else as you're going down. So at the moment, I'm putting together a video. Like, he's done the dive, and I've got all the data, everything back. So I've been messing around with the best way to make a video about the integration behind working out your depth in the ocean.
I'm sure you could work out some way of talking about substitutions and
Hey, that's why I'm workshopping it with you now for just quality jokes. I'll put that in the title.
Excellent.
YouTube will light up. We've got another interesting question here. It says, Matt, ampersand Hugh, so that's us. What was the most satisfying result you have arrived at, either for a video or not? And I think I've got a very, if I interpret the question very loosely, I think I've got some answers for stuff that hasn't made it into videos yet. But I'd also like to get your take on most satisfying result. Because there's been very satisfying experiments that we've not managed to do yet. Like, we've not managed to get a massive turntable to do Coriolis and
oh, I found one. I found
you
one.
sent me a photo. Just but you know, you found one. You walked past a random house in Cambridge and took a photo of their front drive. So yeah. Strictly speaking, you found one.
No. Somebody I know walked by.
Oh no, that wasn't even you.
No, we should definitely do that. We should go there. We should go there with a crate of Vegemite and say, look, I'll give you this.
Bang on the door.
If you let us do an experiment. Yeah, because that's what we want to do. Is this is about the Coriolis effect, and the idea is that if you're on a turntable and you're standing right in the middle of the turntable, you're not, and the turntable's rotating. You've got no sideways. You've got no speed, but as you walk towards the edge of the turntable, you're getting faster. So there must be a sideways force to accelerate yourself. Turns out that it makes you fall over. So we should do a bit of falling over on a turntable, I think, Matt.
That'd be good fun. If anyone watching knows where there's one of those like car rotating platforms, let us know. Save us banging on a stranger's door and having a very awkward conversation. I mean, that said, I just cold wrote a letter to the people who live in Bays's house in Tunbridge Wells and said, hey, a famous mathematician lives in your house. Can I come and film? And they're like, come on in. And turns out their son is like a big maths fan. And so myself and Hannah Fry showing up to do Bayesian experiments, they were quite happy to let that happen. So
what's that
maybe
one?
We could bang on the door.
What's that one? What is that? Bayes watch. Sorry. Okay. Satisfying result. You know, one satisfying result I thought we did in our video, which was, remember that one about the pencil?
The pencil on an edge. Yeah, that was great.
Well, I just thought that was quite fun. Where what you do is you take a pencil. I'm going to go over to my my other view here, and so I've got a table here, And I'll get a bigger pencil because the normal pencil might not be so visible. So
how big a pencil have you got?
I don't have a bigger pencil, but I just get something which is which will do anyway. So look, I've got a slide rule. This will do for a pencil, right?
Okay.
So if I've got this pencil sitting on the table here, and if I give it a whack at the base,
you're still a fair way back. For anyone who's unable to see, here we go. That'll do. So there's a pencil on the edge. Is that acceptable?
I'll zoom in a bit here. Physical zoom. How's that?
That's good. Yeah, I'm happy with that.
Right. So I've got my so-called pencil here.
Yeah.
And if I whack it here,
yep,
it clears the table quite fine. It spins away. But if I don't hit it hard enough, it's going to hit the table. There we go, hit the table.
Yep.
And the question that didn't hit the table, and this does hit the table. The question then is, what is the angle of the pencil to the horizontal when it hits the table, if it just hits the table? Now, I'm not going to go through the maths on that, but I just thought that was really neat because it comes out
online. Yeah.
It comes out to be it's something like what was it? Tan theta equals theta over 3 or something like that.
Something like that. Yeah, I think it's a third. Yeah, tan theta's.
I just thought that was. It's just such an unimportant thing to know, but I thought it was quite good.
The ones I find the most satisfying, and this is probably me integrating like a physicist, is the ones where you model a system fairly roughly, but then everything cancels out neatly and you make some approximations, and then you get a really nice, simple answer that's not dependent on much and it matches what happens in reality. So stuff like that I find deeply pleasing.
Well, there's an example. Some of our first year engineering students at the moment, if they're watching, they will know this question, which is really annoying, which is that if I've got a bottle full of some gas in it, let's say it's got mass M of gas in the bottle, and it's at a pressure P, right? And now if I fill that bottle up from a gas main, so this gas main has got plenty of gas in it. It's like
this is infinitely large gas pipe. Yep.
Yeah. So I open this tap and I increase the pressure to 2P, double the pressure. It turns out that the mass in the bottle goes to 1.4 M.
What?
And 1.4
root 2.
No, 1.4 is this thing for air, and this 1.4 is a thing called gamma, which is the ratio of the specific heats of the air. Anyway, it's all sorts of ridiculous stuff. Yeah, exactly. But the point about it, yeah. But the point about
I refuse to accept that.
You speak to any of our first year engineering students. The point about it is it's about 2 pages of bloody algebra to get this crazy answer that the amount that it goes up is, oh no, that's not quite right. It's 1 over gamma, I think. Anyway, something like that. It's 1 plus 1 over gamma.
I don't know what to believe anymore.
Oh no, look. Anyway, there'll be some engineers somebody in the first year will put the right answer into the chat. But the other thing that I think we ought to do a video on is, where does the number 7 crop up? Because if I take a ball, and I throw it down at an angle onto a table, and then the ball comes down here at a certain speed.
Yep.
Well, I'll just say this: the horizontal speed, I'll call it V. It then starts to spin, and it comes up at a steeper angle. So the velocity over here, I think, is 3/7 of V. Where do you get sevens appearing in maths all on their own. I think we should find where in maths do you
I've
get
just
seven?
searched in my document of videos we want to make, and I've got something called the 2/7 mystery.
Yeah. Yes.
And underneath that I've written ball in infinite table. I'm not meant on. Ball in a tube and ball on a turntable. I've got them all under 2/7 as a heading.
Yeah. So if
that must have been a late night, that one, because I don't
Yeah.
remember entering that in my notes.
Well, I could. If you take a tube, and I don't know whether you might. I always have tubes around, but I might think about this. If you take a tube like a hole that a golf ball goes in, and you toss a ball.
Oh, yes.
And you toss the ball into the tube, the ball goes down the tube, and it goes up, and it comes out again, which is really annoying. Golf players hate it. But if you make the tube long enough, the ball goes down and up. It goes around in a kind of up and down.
Oh, okay. Yep.
And the period of up and down motion is root 2/7 of the period of the orbiting motion. So if this orbiting period is t, then the up and down period, or I think it's root 7/2. Then the up and down period t1 is root 7/2 of t. So
okay, so it's long. It makes sense because it's longer than the.
What do you mean it makes sense?
Period.
Where does root 7/2 ever?
No, I mean the other way up. I was like, how is it doing it faster than the normal orbit? But when you flipped it to the other way up, I'm like, oh, that makes more sense. It needs to be a bigger number than the standard orbit. Oh, there you go. We should do that then. We've got to take that off our list.
Yeah, well, that list is ever expanding.
Oh, really is.
Now, look, what do you reckon? One thing I wanted to do today is to weigh a brick using a tennis ball.
You know, I was going to mention that because that was the first video we did, was the old brick and tennis ball, and you've come up with a new practical use.
Well, it's not really new, but it's just that if I've got a tennis ball, which I reckon weighs 60 grams. That's roughly what it is.
I'll believe that.
And I've got a brick. And the brick, it's definitely a brick.
Oh, it's a real brick. Yeah.
Brick's a lot heavier. Now, if I go to my other camera again, if I were to do an experiment of brick versus tennis ball, then we'll find that
my money's on the brick. Yeah.
Brick wins. But if I do my good old centrifugal force stuff and I spin the ball around like this, I get to a point where the brick is being held up. Yep. Now the question is 1, 2, 3, 2, 2, 3, 3.
I was just about to say, do you want me to count these for you?
Exactly. I reckon I'm doing 3 revs per second, roughly. And I reckon that the radius of the count is about 80 centimeters or something, not quite a meter.
Right.
And what I love about this is you chuck that just that data. I mean, why should anybody ever be surprised when maths works, physics works? So I know that the weight of the brick has got to be equal to this centripetal force, which is mr omega squared. And if that mass is 0.06 kilograms, this radius is 0.8 meters. And this, what did we say? It was 2 pi in 1/3 of a second. And if someone wants to put those numbers into their calculator to figure out what the weight of that brick is and put that into the chat, I'm going to weigh the brick. So let's see who's going to do 0.06 times 0.8 times 2 pi over a third squared, while I find where my scales are. And right, here are my scales. Right, here are my scales. Put the brick on the scales. And look, it says 1.7 kilograms. You see, that's what my scales say.
Hang on, we haven't got a number in the chat yet. What was it? It's 2 times pi divided by 3, was it?
Well, divided by
a third. That's where I went wrong.
Because that's a.
Why would you divide by a? Honestly,
you can do whatever you like. Anyway.
Why would you divide by a? I mean, no offense. Okay, times 0.8 times 0.06. I must have been off by. I've got 17 kilos. So
no, that's you've got 17 newtons.
Divide that by. Wait, what latitude are you at?
You are. I'm at the latitude I'm at. Okay. So
right. I've had to approximate it as 9.81. Yeah, I got 1.74 kilos.
Okay, and so actually, if I actually measure the weight of the brick, I can't really see that very well. Let me just unclip that. Can we see that? Oh, sorry about that. It's very uncool. Not bad.
Not bad.
So I just think it's quite fun. You can weigh a brick with a tennis ball.
That is very cool. Within, a reasonable percentage.
And look, it's even weighing it to 4 significant figures.
Well, there you know it's good. Have you seen? I didn't deliberately grab this, but when I went to grab a drink of water before we started, I went and grabbed a drinkulator, which is a glass that does calculations for you.
Go on.
So if you have a look at the line of the water, see at the moment it's crossing. I need it to be 50 times 1.5. Oh wait, wrong way up. So here we go. So now 50 divided by 1.5 is just over 30. So you can actually use the 3 intercepts on this plot. Will do basic calculations for you.
Where did you get that from?
The one on the back. James Grime designed it. Isn't that cool?
A drinkulator.
A drinkulator, yeah. And so the reason it's on a mason jar is not because I'm a hipster. I mean, jury's out. But because for it to work, it had to be on a flat surface. The curvature, we tried to compensate for the curvature of a glass and we couldn't get it to work. And so we ended up doing it on a flat.
And does it have to be filled up to exactly the right? Does it have to be filled up to exactly the right level of water?
No, any amount. You can move the line wherever you want, and it will do a valid calculation between the 3 points. The 3 points where it's intercepting the cubic.
There you go. I like that.
Yeah, isn't that amazing?
So now, one question that always crops up is, what's the latest of pi? What's interesting about pi? Because you wrote a book about pi, didn't you?
Humble pie.
What's your?
Someone has asked what our favorite constants are.
Yeah. Okay. What's your favorite constant?
Pi. That was easy. I mean, 2/7.
One thing that I think is quite fun about pi is that when you're thinking about global warming, as you do, that the ratio of the mass of CO2 that comes out of a hydrocarbon to the mass of the hydrocarbon, well, it's really quite neat, because if I think of my hydrocarbon as looking like this, a long chain of
hydros and carbons.
Hydros and carbons, like this sort of thing. If I just take one of those, that's got a molecular mass of 12 plus 2 is 14. And that, when it burns in oxygen, becomes CO2, which has a molecular mass of 12 plus 32, 44. And 44 over 14 is 22 over 7.
I'm disappointed in you, Hugh. Yep.
So pi, and you can't do that with tau, can you? Right, I rest my case.
First you're integrating a sine wave. Now you're setting 22/7 equal to pi. Although actually we do, because I calculate pi once a year on Pi Day. And I alternate between doing a calculation by hand and doing a physical experiment.
Remind us, which day is Pi Day?
Pi Day is the 22nd of July, because it's 14th of March, because it's in the American writing, it's 314 when you do for some reason, the month followed by the day. So we've just had Pi Day. This year, I used Avogadro's number. So if you put a drop of, it's not oil, it's a surfactant, something that spreads out to form a single molecule thick layer on water. We put a single drop of oleic acid onto water, measured how big a disk it formed, and we knew how many molecules there are using Avogadro's number. And so we used Avogadro's number to work out the area of the disk, and we measured the diameter, and then we rolled back to get pi. And so we were able to derive pi from Avogadro's number.
Where normal people derive Avogadro's number from pi.
I know. That's been done. But 2 years from now, I'm going to need another, because next year I'm going to do a by hand calculation. I need another physical experiment I can do. And we talked about doing like compressing beams or something, but I'm always open for more physical experiments that can be used to derive
Isn't
pi.
there an experiment where if you were to drop a toothpick onto some lined paper, so if I get some lined paper, and well, didn't somebody make a cake with twiglets in it? And then wasn't this at Maths Jam or something?
I think someone did it at the Maths Jam baking competition. So Buffon's needle is the name of that experiment.
What's it called?
Buffon's needle.
Go on.
I think I could be mispronouncing
go on. What's the experiment?
It's the classic. Give me a second, and I'm sure a lot of people have come across this previously. It's if you've got. Actually, have I got a stick? I'll use. I'm going to use. No, that's not going to work as a generalized stick. Let's say I'm just going to draw a bunch of parallel lines on my page here, and let's assume these are perfectly straight and perfectly parallel and equally spaced, as that are, right? And then if I was to start dropping sticks, which are the same length there as the gaps between the lines, so they might randomly miss the lines, they might randomly fall on a line, but if I start dropping loads and loads and loads of these at random, the probability of them landing on a line compared to not on a line is pi on 4. And so if you do this experimentally, I think it's pi on 4. Let's go with pi on 4. So if you do this experimentally, you can drop loads and loads and loads of sticks on straight lines, and then you can work out an estimation of pi by rolling it back this way. And so I think what the person at Maths Jam was doing was having the sticks as if they're falling in the cake, and where you slice through them, it's the way of putting the straight lines. And that
I seem to remember that every time you cut a slice of the cake, you had to write down on a piece of paper how many of these twiglets, whatever they were in the cake, you could see in your slice. And this was
for context,
estimation of pi by afternoon tea.
Pi by snack. Yeah. For people at Maths Jam is like, it's a monthly meeting where people do maths in the pub. There's also like a big annual weekend where everyone gets together. And at the Maths Jam weekend, there's a mathematical baking competition. And so people bring all sorts of weird math-based baked goods, and there are prizes. And so that's the competition that someone entered that cake in.
And there's also, there are other competitions as well. And then there's a competition for the best competition. So there's a competition.
Yeah. And
this gets a bit recursive.
We think it's pretty funny. I've just noticed we've hit 8 o'clock. I'm not sure if Sam wants to chip in and tell us when we're meant to stop talking and let people get on with their lives.
Okay, sorry, I was struggling to unmute then. I think it's fine if you keep going. I mean, I don't think anyone's just going to drop out.
We could answer a few questions.
Well, should we do a few quick questions? Someone's just written mass is almost square root 3. Oh, is that the brick? 1.7.
Hey, there we go. That's pretty good.
Good observation, someone. Someone says that Drinkulator is so cool. Is there a merch store? I think we've got it on Maths Gear. Give me 1 second. The arguments we had over the name of the Drinkulator. Oh, we do. We've got it on. Is it in stock? Let's just check before I. It is in stock. There you are. That was not a deliberate plug. I've just got a whole bunch of them in my office because I have a lot of Maths Gear stuff kicking around. So I'm going to paste that into the chat. There you go. Other names, the Thinky Drinky. That was up there with the best of them. But I think Drinkulator won out on the argument.
There you
go. Yeah. Someone just says engineers, yay.
I'd agree with that one.
Someone says making the same mistake as Matt is kind of cool. I mean, get on board. There's a lot of mistakes to go around.
Well, is that people saying forgotten about Newtons?
I forgot about Newtons. And people are saying if I'm a true engineer, I should have used G equals 10. So I will accept little known fact, I mean semi-known fact. I did half an engineering degree before I realized it would leave me dangerously employable at the end of it. And so I got out halfway through my mech eng degree, and then I moved more abstract before I finished my degree.
Well, we love you.
Yeah, yes, I feel semi-accepted in the engineering world, having given it a go and then switched to mathematics.
So well, I first met you when you were on stage at the Royal Institution as the warm-up act. The warm-up act.
Oh, yes. Yeah.
With Chris Bishop. And you were doing something about cubed roots.
Yep.
And so I can't remember what that was, but you could do cubed roots of numbers.
Yeah, it's a performance trick. So I can do a thing where people cube a number on their phones or a calculator, and then they give me the answer, and I calculate the cube roots in my head.
Is this how many digits in the number? I
can do 2-digit numbers cubed.
Okay.
I can. Yeah, oh goodness. Okay. Yep.
All right. So I've got a number here which is 185193.
Sorry, how many thousands? One. Oh, 57. Or is that on there? 185,000.
How did you do that? How did you do that so quickly, or is that a secret?
So I know if it ends in a 3, the starting number had to end in a 7, because if you cube anything with a 7, the answer will be a 3. 7 cubed is 343, and anything ends in a 7, you cube it, it'll always end in a 3. And I know that 185,000, it's bigger than 125,000, which is 50 cubed, and it's smaller than 216,000, which is 60 cubed. And so I know it's in that range. So I know it must be 50, 57.
Okay, right. Close your eyes. Close your eyes. Okay, so everybody can see what I'm doing here, but you can't. Okay, that's your number. Open your eyes. Open your eyes.
Well, 405,000. That's 74.
Ah, you geek.
Yeah. The issue is, if people give me all the digits one at a time, I have to wait until the end before I know what positions they all were. And so when they come at me too fast, I'll often miss how many digits. So I don't know, because all I'm really doing is using the size of the number at the beginning. And so something like that, it's easier if it's written down, or I get people to say, 405,000 and whatever. And then
you can do missing digits on barcodes, can't you?
I can do missing digits on barcodes.
Let's do that another time.
This has just become a Hugh request. Matt does tricks hour.
What else have we got to wind up now? We ought to wind up, I think. What else is there?
Someone says in natural units, all the best constants are 1. That is excellent. Excellent
Wow.
work, person. There you are. One of my favorite. I've been tempted. You know, we said Pi Day is on the 14th of March because it's 314. And Pi Approximation Day is the 22nd of July because that's 22/7. I've always been tempted to have like astrophysicists Pi Day on the 10th of January because I remember doing in astrophysics, pi is equal to 1 and pi squared is equal to 10. And so I keep thinking we should have a cosmology Pi Day on the 10th of January to celebrate rounding.
Well, that's, I mean, I do,
magnitude.
this is me being an engineer again, but I do find that G, gravity, being pi squared is very handy.
Yeah, because pi squared is 9.87.
It's great.
So
it's also
super close. Yeah.
That's perfect. And I think the kinematic viscosity of water or of air, I can't remember, is 1 acre per fortnight.
Oh, really?
Mm.
Acre per fortnight. Units. Let's not get onto dimensional analysis. That will be another hour of our time. This is why we end up we stay up too late, because we often meet up the night before we're doing a show together the next day.
And the show is much the better for it, particularly after a few pints.
Oh my goodness, we are at our alert best the next morning. So anyone who has seen this has been morning show.
This has been great fun. It's a poor substitute for meeting up together over a pint or two. But it's been great fun, Matt. And I just want to say thanks to Sam and everybody from the Trinity College Engineering Society for inviting us to do this. Well, we should do it again.
Yeah. And if people want to look at the coin flipping data, send me an email.
Excellent. I thought you said you already got too many emails.
No, I get emails from people saying, when are you going to do another video on it? But I haven't got the time to go through it all. So if people want to give us a hand, mathematical fame and fortune await.
Very good. Over to you, Sam.
Yeah, okay. So I think we're going to wrap up the stream now. So I was watching all of that, and I got a bit scared, Hugh, when you started doing some slightly dodgy integrals in front of Matt Parker here. Didn't want to tarnish the reputation of his in any way.
Too late.
And then when the brick was going around your head.
No, the brick wasn't going around my head.
Oh, well, the ball was going around your head, but the brick was in front of you. I mean, also a bit risky. So thank you both for coming to this event. I think it's been a really tough term for a lot of people, and this is the kind of the cheerful thing at the end that I think a lot of people look forward to. So thank you for coming, and I think we'll probably close the YouTube stream off now.
Great. Well, thank you very much.